Okay, in this video we take a look at another form of energy called GPE, gravitational potential energy. Now perhaps you have this slide that's next in your packet and you're expecting that I'm going to talk through this first. I'm going to skip over this slide and the next one and go right into this in here called potential energy. So let's go ahead and start there. Now before I get into this particular slide, I just again want to refresh your memory on the various forms of energy that we started our unit with. We have energy stored in movement or energy stored in position. We already talked about kinetic energy. That's the energy of large-scale objects. Now we're going to look at various forms of potential energy, and we're going to start with GPE. It is due to position in a gravity field. Let's go ahead and now formally define gravitational potential energy. So we're at this slide, finally. Potential energy is due to position of an object within a system. And when I talk about a system, you'll see what I mean down here when you look at this wrecking ball on the Earth. It can be considered stored energy, and the reason we consider it stored is that it really isn't energy in motion, at least not yet, but it does have the ability to do work or transfer energy when its position changes. Gravitational potential energy, often just called GPE, is probably the most common form of potential energy that you would be familiar with. It does belong to a system. It's usually the object and the Earth. And if you think about what's happening here, this wrecking ball would have a tendency, if that chain were to break, would have a tendency to fall straight down to the Earth and maybe do a lot of work down here. If it wasn't for the Earth pulling on that wrecking ball, we wouldn't say that that wrecking ball has any energy at all. The only reason it exists is because the Earth is pulling on it. So we need a system of objects, and in this case, that system would be the Earth and that ball. Now, it is equal to the amount of work needed to move an object, a height h, within a gravity field. So we can think of the work equation. Work is equal to F times D. In this case, that force is the weight of the object. That G right here is due to the fact that the Earth is pulling on that with a gravitational field strength of G. If there's no Earth, there's no G. That means there's no potential energy. Now, D is the common unit that we use for work. It's whatever distance we've moved the object. If we're lifting an object, a height h, let's go ahead and just replace D with h. Fairly simple equation, GPE, mgh. Again, GPE is measured in joules. It is a form of energy. Mass needs to be in kilograms. G should be in meters per second squared, or newtons per kilogram. And then height would be in meters. Let's go ahead and see how we could use that equation in just a few examples. So the wrecking ball has a mass of 125 kilograms. It's 5 meters above the Earth. How much GPE exists between the ball and the Earth's surface? So up here, if I drop that ball, it's going to tend to change its position downward, and I want to determine how much energy it has at that position due to the fact that it's elevated above the surface of the Earth. We just simply plug in some numbers here to be able to calculate that. 125 kilograms is our mass. It's over 250 pounds. It's a pretty good wrecking ball. Let's use G to be 10 newtons per kilogram. Just easier to calculate than the 9.8. And we're currently 5 meters above the surface of the Earth. When we go through and do that math, we get about 6250 joules. So the gravitational potential energy associated with that ball at that position, 6250 joules. Now what does that mean? If we define, again, gravitational potential energy as the amount of work needed to move an object, a height h within a gravity field, we could say that if that wrecking ball were here, we would have to do 6,250 joules to move it up there. Now when I say it's stored work, if it's stored energy, if I do that work to lift it up here, if I just cut that chain, I'll get that work back, and we'll be able to turn that stored energy back into something else that might be useful. That's what we mean by stored energy. Let's take a look at 6 equal-sized books on Carlos's bookshelf. Each book weighs 17 newtons. How much GPE do these books have if they are 2.3 meters from the ground? Again, somewhat of a straightforward calculation. GPE is equal to mgh. I see that I have 6 of these books, and each one weighs 17 newtons. So when I go through to calculate this, that 17 newtons is actually m times g. Let's use some color coding to make sure that we keep track of some things here. That right here, that 17 newtons already contains that g in there. I don't know what the mass of those books are, but I know their weight. So I have that. Now the 2.3 meters is just simply that height, and I have 6 of those. So now I just go through and calculate that. And that's about 234.6 joules. If those books were on the ground down here, and I wanted to lift them up to the bookshelf, I would need to do that much work. If they fell off of that bookshelf and fell down to the ground, they would be able to do that much work on whatever it is they hit on the ground. How high must a platform be so that a 56 kilogram diver does 2,300 joules of work on the water as they fall? So if they're up here and they have some water down here that they're going to jump into, they have gravitational potential energy up here, and that's equal to 2,300 joules. I want to know how high up they need to be such that when they change that gravitational potential energy into other forms, that they'll be able to do that much work under that water. Again, that's how we define gravitational potential energy. If that person were to climb up a ladder to get up to that point, they would have to do that much work to do so. So let's go ahead and calculate that. 2,300 joules is mgh. I'm looking for h, so I take 2,300 joules. Let's see, he's 56 kilograms. And g, let's use that to be 10, and then solve that for h. So 2,300 joules divided by, let's see, that's 560, and that would be that height. And so 2,300 divided by 560 is about 4.1 meters. Not too bad. Very last one, a little picture here to see if you can understand gravitational potential energy along a staircase. If we have this ball here, it's got 0 potential energy relative to the ground at that position, and I go all the way up here, I see that it's got 50 joules of potential energy at the top of those stairs. Could you identify how much energy it has at each one of these positions? Could you identify the potential energy at each of these spots? I want you to think about that for just a moment. You can see, since we have an mgh in there, and mg stays constant for that ball, in order for me to sort of equally divide that out into those 5 steps, each one of those steps would change the energy by about 10 joules. So 10, 20, 30, 40. And there we go. Not too bad. I'm sure that you see that gravitational potential energy equation is actually pretty easy to work with. And that completes the video for GPE.